So today's class is about the normal distribution, and to do so, we first are going to introduce or talk about the difference between discrete and continuous distribution, introduce the concept of probability density function, write the probability density function for the normal distribution, and use that to solve some very simple introductory exercises. So all the distributions that we have dealt so far in the course are discrete probability distribution, right? Both binomial and Poisson allow you to solve for the probability of a certain number of your events, right? So if you look at here, for example, here we are plotting a histogram, right, corresponding to the probability of success, for following a binomial process with 20 trials, and the probability in the per trial probability of success p equal to 0.5, right? And if I ask you guys to determine what's the probability of having 7 positive successes, you would come down and tell me it's about the height of this bar right here, right? When we're dealing with continuous distribution, things are a little different, right? So the continuous distribution, rather than having a histogram, we actually have a curve, right? Because basically the continuous distribution span the value numbers that are real, right? So we're decimal. And so in this case, we cannot define the probability of x exactly, right? The probability of x cannot be defined, but we use the probability as the part which is included between 2 points under the curve, right? So just to summarize, for a discrete distribution, we can calculate the probability of a certain value as the product between the height of the bar and the bar width, right? And this makes sense because, if the probability, if we go here, if we go into a histogram, right, where this is your bar associated to your variable x, where this distance is 1, right? The probability is going to be exactly this. It's going to be your y times 1. It's your probability, right? In a continuous distribution, instead, we don't have this, right? We don't have a histogram, right? We have a line, such as here. We have a line, and so the only way that we can define the probability is by defining two intervals, right? A and B, and determine this area right here, right? If you remember calculus, the probability, the area under the curve, P A less than X less than B, right, is the integral, right, between A and B of what? Of your function fx in dx, where this is x and this is fx, right? So the curve, it's your fx, which is also called probability density function. The probability, right, which is the chance of finding an observation which is contained between two values a and b, is the integral between a and b of your probability density function, okay? So, right, so this is just to summarize. In a continuous case, we need to take the integral, right, to get the value of the chance that x is included between two minimum and x maximum between two extreme. In the case of the discrete density functions, for example, binomial, you actually calculate the area that's which is the height of a certain bar. So the normal distribution the most famous example of continuous distribution, right? It's a normal it's a symmetric distribution that is described by two parameters, the so-called mu, mean, and standard deviation, sigma, right? When we say that x is a random variable which is normally distributed with a certain mean and a certain standard deviation s, we use this notation. We say x is normally distributed, n stands for normally distributed, with mean mu and standard deviation sigma. Okay? So the probability density function, which is the equation, right, that allows you to draw the bell-shaped curve, right? This is the P, D, F for different values of x as a function of the two parameters, right? The mean and the standard deviation, right? Is this one. This is the probability density function, or is the normal distribution curve. Okay, note this, it's not your probability. The integral under this curve between two different values of x is equivalent to the probability that the observation fall between those two values. Okay, so just to give you an idea, a very simple example of the normal distribution, right? So, you know, same mean but different standard deviation, right? We see that the distributions are peaked at the same value, but the spread is different, right? Higher standard deviation means a more spread distribution, and the lower lower height for your peak. And then comparison between same standard deviation and different mean, right? We basically see the same distribution, which has been shifted towards the right? If we go here, right, the peak has been shifted at 130. Okay, so what's a few things to remember is that the peak of the normal distribution is exactly the mean, right? So the normal distribution is symmetric with respect to the mean, and we will see later that how useful. A couple of other important things. We know that 68.26% of all of your observation, if your random variable follows a normal distribution, are found between plus or minus one standard deviation, right? So 68% of your data is gonna fall within plus or minus 1 sigma. 95% of your data is gonna fall between plus or minus 1.96 standard deviation, and then and so on, right? So this is very important because it's gonna be useful for the estimation of confidence interval. And the idea is this one, right? If this is my normal distribution, right? Here is my mean mu, this is mu plus 1.96 sigma, this is mu minus 1.96 sigma, this is equivalent to 95%. Okay, so and this is exactly another way of representing those areas. Now you guys can understand that there is infinite normal distribution, right? Because why? There's going to be an infinite combination of mean, mu's, and standard deviation sigma, right? So how do we do that? So there's one special normal distribution, which is the normal distribution to which we always fall back, right, with a method that we call standardization that we'll see later, which is called the standard normal distribution. The standard normal distribution, z, or standard score, it's a random variable which is centered at 0 and has a standard deviation equal to 1, right? So we can use the standard distribution to start basically making a few probability calculation. For example, given z to be a normally distributed random variable, mean center in 0 with standard deviation equal to 1, what is the probability of getting a value z that is less than 0, right? This is basically equivalent to finding what? To finding the area, right, which is covered by your distribution that goes from minus infinity and 0. Minus infinity and 0, right? And the other example, what is, we know that this is basically 50%, right? Because we know that the entire area is 100%, so you can basically see without even checking anything, you're gonna say, okay, I have 50% chance that the value is between minus infinity and 0. What about the probability of finding an observation which is less than 1, right? So again, I always advise to basically draw the distribution and shade the area. The idea is that the probability is going to be finding the integral between minus infinity and 1 of your normal PDF, right? Which is the equivalent of estimating this area, okay? So, of course, we don't know, right? How much is this, right? We know that this is 50%. This is 50%. But we don't know how much it is, right? So either you have a computer, right, and you can integrate, or you can do this in R, and R spits it for you the exact value, right? But when people didn't have R, what they did, they actually tabulated this. They tabulated the area, right, of your under the curve or of your standard normal distribution. Depending on the type of book that you have, there are different ways, right, that people have tabulated. For example, in table A1, which is the table that we use from our book, what the book reports this area here, reports the area from 0 onward, right? So report this area here, right? So we know that from minus infinity to 0 we have 50%, right? So the probability that x it's less than 1, right? It's gonna be 50% plus what? Plus, I'm gonna go here, this is 1, so 0.34 plus 34.134%, which is about 84%, as you can see later, right? Now other books have different other of tables. You can see if they're online that there are other books that actually report the area going from minus infinity. So other books are actually reporting assume this probability, assuming that this is 1, right? So if you are using a different books, which is not the one from our class, you would actually, and it has this type of table, you would actually directly infer the value by reading the table. Okay. So, as I said, there are given mu and sigma, there is an infinite number of possible normal distribution, right? But we don't have an infinite number of tables in our book. The idea is that you can apply a concept called standardization to go from an x to z, right? So you go from a random variable which is normally distributed around the mean mu and standard deviation sigma to the corresponding standard normal distribution z, which is distributed around mean 0 and standard deviation 1, right? So the z-score, how do we do this? We do basically by so-called standardizing your data, which means by subtracting from your observation the mean and divided by the standard deviation, right? So this is called standard score, and it basically it actually represents the distributions of the distance of your observation from the mean per units of standard deviation, right? So let's do a couple of examples to better understand this. We know that the length of human pregnancies from conception to birth follows a normal distribution with mean mu equal to 166 days and standard deviation sigma equal to 16 days. What's the probability of finding a pregnancy that is as long as, that is more, or that is long at least 240 days? So let's draw our thing, right? So this is 266. Okay, so let's assume this is 240. We want to know the length of the probability that the pregnancy is at least 240 days, right? So we want basically this area. We want the probability that x is bigger than 240, right? How do I solve this? So the probability that x is bigger than 240, right, is equal to the probability that z, right, doing standardization, is larger than 240 minus the mean, 266, over 16, the standard deviation, which is equal to the probability that x is larger than minus 1.625, right, which is basically a point right here, which we don't know, right? We cannot calculate this area, right? The book gives us up to a certain value, right? So this is going to be equal, because the distribution is symmetric, to 1 minus the probability that z is less than 1 minus 1.625, right? So if we look at the table, the probability of 1.625 is 0.05 to 1, so 1 minus is about 94%. Great. So a second example, the height of young woman, from 18 to 24-year-old, it's about normally distributed with mean of 64 inches, a standard deviation of 2.5 inches. What is the probability that if I select a woman at random within this age range, its height is between 55.9 and 67.5 inches? So the probability that x is between 55.5 and 67.5 gets transformed into z-scores, right, is equal to the probability that the z, my standard score, is between minus 1.8 and 1.4, right? So this is minus 1.8 and this is 1.4, right? Which is equal to what? Is equal to the probability of being less than 1.4 minus the probability of being less than minus 1.8, right? So the probability of being less than p of x less than 1.4 is equal to 0.9192. P of x less than minus 1.8 based on the table is 0.0359. Therefore the area in between these two is about the subtraction, which is 88%. Okay, so these are the ways of how to use the z table, right, to find probability. Now the other option is this one. Let's assume I know a certain probability. I want to find the corresponding x value, right? For example, what is the value that corresponds to the top 10% long, or the longest 10% pregnancy? This is question number 1. or another type of example. What is the third quartile of hatching weights for chickens at birth, right? So let's go back to the first question, right? The length of the human pregnancy, we said, is normally distributed with mean equal to 166 days and standard deviation of 16 days. How long are the longest 10% pregnancies? So the problem here has to determine the x value that corresponds to having 10% of the normal area on its right? So basically what we want to know is what value of x has the probability here of 10%, right? This is equal to what? It's equal to the value of x that had on its left 90%, right? Which is equal to the value of z that has on its left, so this is 50%, 40% from your table, right? So what value of z in your table has 40% here? So if you go on your table, you're going to find out that z is equal 1.28. At the value of z equals to 0.28, we have covered 50% plus 40%, right? So because z is equal to 1.28, right, and we know that z is equal to x minus mu over sigma, right, we can rearrange our equation to calculate x, which is equal to z sigma plus mu, right? So x is equal to what? 1.28 times 16 plus 266, which is equal to 186 plus 48 times 48, right? So this value here is the value that corresponds to the top 10% 10% longest pregnancy, right? So the final example is about hatching weight of chickens, right? We know that at birth chicken hatch with a weight which is normally distributed with mean equal 45 and standard deviation is equal to 4. What is the third quartile of the distribution of hatching weight, right? We want to know what's basically what value corresponds to have x, where this is 75%, okay? So if we go look at the table, right, what do we find? We find that at the value of 0.67, I have an area that's basically corresponding to 74.86%. At the value of 0.68, I have an area that corresponds to 0.7518%, right? None of these two values is exactly 75%. So what do? The idea is that I use some linear interpolation, right? So how do I interpolate? I say that delta x, linear interpolation, you guys should know, is equal m times delta y, right? So this is the value corresponding to 7518. This is the value corresponding to 7486, right? So if I do delta x over delta y, I have m, right? Once I calculate m, I can bring it back here and use, for example, the data for 75% and for example 67 and 74.86 to calculate the value of z star. Z star is the value at which you have 75% cover in your standard normal distribution. When you know Z star, right, which is this guy here, you go back using your standard equation, right? You rearrange it and you can find your X value. So 47.6972 grams is the third quartiles for weights for chicken at birth. And so this is it for this class.